Questions?
Could we go over 8? I wasn't able to do that.
Yeah.
Also, the solutions were not the solutions or something.
They were to different problems or something?
Yeah.
Okay, so these were uh, what topics? What topic was this? Okay, incompressible, ideal. That was the old ones. This one, determine the percent error.
No. There, 8 was the last one. Yeah. You wanna? Hmm?
I'll I need to copy it, so I need to find it anyways. Okay, so it's neither of those.
It's the one with the O2 gas. Because, like, I thought we needed to choose the work with expansion, but then we don't even have any of the volumes.
Okay, so we know the mass of O2 gas. Uh, we have information about it. And so let's see. We have okay. So we're going to do this as an ideal gas. Um, it's allowed to expand until it gets to a certain temperature. Um, it's a polytropic process. What's the work? Okay. So we're going to start with P little v is equal to RT. Um, it's O2 gas, so the mass per mole is 16 times 10 to the minus third. You'd look up the 16 on the periodic table, and then you'd just have to switch from grams to kilograms. And so R is equal to 8.314 divided by 16 times 10 to the minus third. Um, oh, and no, this is so M for oxygen would be this. Um, that means that M for O2 gas would be 32 times 10 to the minus third. So you get 259.81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. 81. now put it into the ideal gas law. You have 2 times 10 to the fifth times the specific volume is equal to 259.81 times the temperature in Kelvin, 80 Celsius plus 273, so that's 353. And so the specific volume is 0.459, and that's cubic meters per kilogram. This is at state 1. If the first thing we're trying to figure out is the work of expansion, we know we're going to try to do this integral with respect to true volume. And so I want the true volume, not just this specific volume. So the true volume is this times 0.4, which is 0.183. And it's allowed to expand. So we don't know what the final volume is, but we do know now that we have the pressure and the volume, we can use the polytropic process thing. So we have that 2 times 10 to the fifth times 0.183 to the 1.25 is equal to C. And so C is equal to 23,938.3. And now we can figure out the final volume because we know, oh no, we can't yet. So we have a final temperature of 40. Let's see what we know. We don't know the volume. So we know that P2 V2 is equal to 259.81 times the temperature, which is 313. And we know that P2 V2 to the, this isn't, so P2 times the true volume, which is 0.4 little v2 to the 1.25 is equal to 23,938.3. Everyone with me on that, what I'm doing there?
So V2 is our like little specific volume?
That's right. Little v2, yep. And so we can write this as, so 0.4 to the 1.25. So we can rewrite this as P2 little v2 to the 1.25 is equal to 75,252.1. I just calculated 0.4 to the 1.25 and then divided both sides by that. Okay, so now we got this thing, and it's a sort of an ugly system of two equations for two variables. But we can go, let's see, how do we want to do this? So let's say V2 is equal to, I'm going to multiply that top equation out, 259.81 times 313. And so we have V2 is equal to 81,320.5 times P2 to the minus 1. And now I'm going to substitute that into the second equation. So we have P2 times 81,320.5 P2 to the minus 1 to the 1.25 is equal to 73,252.1. And so we have P2 times P2 to the minus 1.25 is equal to, oh, two, it looks like I just wrote this down wrong. This is actually 75,000. Nothing changed about the approach there, just minor dyslexia episode. Okay, so we got this. And now I'm gonna get rid of this constant in there. So I'm going to divide by 81,320.5 to the 1.25 power. So this comes out to be 0.055. And that is, so that says P2 to the negative 0.25 power is equal to 0.055. And so I want to multiply this exponent by negative 4. So I'm going to take P2 to the negative 0.25 power, and I want to take it to the negative 4th power. So that's equal to 0.055 to the negative 4th power. And so P2 is 109,282 pascals. Okay, any questions about that yet? That's a lot of exponent fiddling, like there aren't a ton of classes where you do a lot of exponent stuff, so it tends to sort of, your memory of that stuff tends to sort of go away. But when we're dealing with these polytropic processes, it's all this kind of stuff. Um, okay, so now we have the two final pressures. We can use that to calculate the final volume. So we can do it like this. I'm going to put it in here. I'm going to say 109,282 times the specific volume 2 to the 1.25 power is equal to 75,252.1. 52.1. And so V2 to the 1.25 is equal to 0.689. And now I'm going to take both sides. I want V2 to the first power. So I'm going to take both sides to the 1 over 1.25 power. So when you multiply those two exponents, you get 1. And so 0.689 to the power of 1 over 1.25. And so you get little v2 is equal to 0.742 multiplied by the mass, and you get that the true volume at state 2 is 0.297 cubic meters. Okay, now we're almost ready to compute that integral. So we know that we have PV to the 1.25 is equal to 75,252.1. And so to compute that integral, we need pressure expressed as a function of volume. So P is equal to 75,252.1 V to the negative 1.25. We're just isolating, getting P by itself. And now finally we can say that the work of expansion is the integral from the starting volume of 0.183 to the ending volume of 0.297 of 75,252.1 times V to the negative 1.25 dV. And so this is equal to, so it's going to be 75,252.1 times V to the negative 0.25 divided by negative 0.25. And so that is negative 301,008 times V to the negative 0.25, evaluated from 0.183 to 0.297. So we have 0.297 to the power of negative 0.25 minus 0.183 to the power of negative 0.25. And then we're multiplying that number by negative 301,008. and we get a work of expansion of 52,474.5 joules. Does it make sense that we got a positive work of expansion? Yeah, it expanded, the volume increased, so that's what we expect. Okay, that's a tricky one. I mean, it just takes fitting a lot of pieces together, like kind of being able to see what you have and plan out your steps, kind of a few steps in advance. Um, the next one shouldn't be so hard. It doesn't look like. So we're saying 1,500 joules is added to the gas during the process. It doesn't even say whether it's work or heat. Um, so 1,500. Let's say it's heat. So then for part B, we're going to say the change in internal energy is equal to Q minus W. And so the change in internal energy is equal to, we're going to say 1,500 joules of heat is added, minus 52,474.5. And so the change in internal energy is negative 50,974.5.
Professor.
Yep.
So the PV equals RT, that's using the specific vote or
Yeah, specific
P,
volume. Yep.
but PV to the 1.5, the polytropic, that's using the actual volume.
Right.
So what was our C constant value?
75,252.1.
Wasn't the pressure 2.0 times 10 to the 5 pascals and the volume was 0.183 meters cubed? Oh,
Yeah. So, right. So, okay. So this is the true volume at state 1, 0.183. And then we had to use the stuff happening at state 2. And we had to do it a little differently than we have had in the past because we didn't know that second volume. We had, so I solved it as two equations for two variables. Here's the ideal gas law. And here's where I use that polytropic equation. The 0.4 is to take it from the specific volume to the true volume. And oh God, I used the wrong. Oh, I'm not doing it again, but
okay.
I yeah.
I was like, okay, it seems like I got it, and then I did work is the integral from V1, which is the actual V1 from
Mm-hmm.
to the actual V2,
Yeah.
and then PdV.
Yeah. So here's where I kept using this as
okay.
I kept using this as C.
I can fix that then, I guess.
This isn't C.
We did it accidentally a little bit.
Yeah. So C is really this.
Mm-hmm.
Okay. And so later on, when I went back to this equation, this should be C. And so my numbers are wrong. Starting at this point, I think. Hopefully that's where it starts.
So is the 0.297 meters cubed that should be right?
As far as I can tell, I mean, I'm just glancing at it, but it looks like I didn't make any mistakes until this point here.
And then the work of expansion is just 16.7 kilojoules.
Okay.
I think. Maybe.
Yeah. Hopefully still positive and stuff. Any other questions about that one? Okay. Let me do, so we're talking about um, control volume analysis. The first thing we talked about with control volume analysis was mass balance. And so let me do a problem or two, example problem using mass balance. Um, so this is back to um, control volumes. Okay, let's say we have a tank that can hold 20 kilograms of liquid water. Um, and it starts with 5 kilograms of water. If the mass flow rate, the rate that liquid water flows into the tank, is 2 kilograms per second, and the rate that it flows out of the tank is 1.5 kilograms per second, and we have two questions. First, how long in seconds until the tank fills? And then second, if the average velocity of water coming in at the inlet is 10 meters per second, and the average water speed leaving the exit is 25 meters per second, what are the areas at the inlet and the exit? Okay, so the mass balance equation says dm/dt, the rate of change of the mass inside your control volume, and our control volume is going to be the tank, the inside of the tank. So I'll write this like this. That's the rate at which the mass in the tank is changing, is equal to the rate of flow in minus the rate of flow out. And so dm dt is equal to 2 minus 1.5. So that's equal to 0.5. And now I'm going to multiply both sides by dt. We've done this a few times. And I'm going to write this as dm inside the control volume is equal to 0.5 dt. And I'm going to integrate both sides from state 1 to state 2. So for dm, uh, we can think of this as, so we're integrating with respect to m. And so these boundaries need to be masses. So we're starting at 5 kilograms and going to 20 kilograms. And over here, we can think of like we're turning on our stopwatch to start timing at state 1. So I'm going to call that time equals 0. And we're just trying to figure out what that final amount of time is. I'll write it as a t. I think sometimes math professors get a little, uh, uh, that's a little cringy to them with the the variable that I'm integrating over as the same variable I have in the boundaries. I really should use a capital T or something, but I didn't think ahead, and so I'm just going to keep it as T. They would probably use tau as like the dummy variable here or something. Okay, so what do you get? So if you integrate this side, you just go 5 to 20. And if you integrate this side, you get 0.5 t evaluated from 0 to t. And so that says that 15 is equal to 0.5 t. And so t is equal to 30 seconds. Any questions about that? So anytime you're using differential forms of any of this stuff, an integration like that is a tool that you have if you're trying to go from a differential form to like a total amount of stuff or a total amount of time. Okay. And then for part B, now, well, we know that at the inlet, the mass flow rate is 2. And remember that the last thing I did last time before the end of class was to say that you can always calculate the mass flow rate as the area of the opening times the average speed of the material divided by the specific volume. And so 2 is equal to, this one says for part B, the average speed of liquid water at the inlet is 10. So we have 10A divided by the specific volume of water. You could look that up in the table or the website for saturated liquid water to find that. You're going to get a value that's very close to 0.001. So if you wanted more precision, you could look it up at the temperature we're at, which it doesn't say what the temperature is, so I'm just going to use that. And so 2 is equal to 10,000 A. And so the area of that aperture is 0.0002 meters squared. Which, if you think of that as like a square opening, would be 1.4 centimeters side length. And now we can do it at the exit. It's just going to be the same approach. So the mass at the exit was equal to 1.5, and that's equal to A times speed divided by specific volume. So 1.5 is equal to, this time we're given that the speed, the average speed of the liquid is 25. So we have 25A divided by 0.001. And so the area of that exit hole is 0.0001 more 0.6 meters squared. It has to be smaller because the liquid is moving faster. And so that's about 0.8 centimeters if it's a square opening. Any questions about that? Okay, so no matter what happens to the material inside that control volume, this mass balance has to hold. So there's no possible way that you can create or destroy mass inside of this volume. Okay, so even if mass goes in as a liquid and comes out as a steam or vice versa, that mass balance equation has to hold. Okay, so let's do one now where we have different phases. Okay, so at the inlet, let's say that steam is coming in. So it's water vapor. Um, the pressure at the inlet. Okay. So this is, so what we have here is more than just different phases. We have two inlets and one exit. So at inlet 1, so at inlet 1, we have vapor, and the pressure at inlet 1 is 7 bar. The temperature at inlet 1 is 200 degrees Celsius. And the mass flow rate at inlet 1 is 40 kilograms per second. Then we have a second inlet where liquid water is coming in. So this is liquid water. So at inlet 2, the pressure is also 7 bar. The temperature at inlet 2 is 40 degrees Celsius. And the area of the aperture for inlet 2 is 25 times 10 to the minus 4 meters squared. And then there's one exit. And at the exit, we have saturated liquid water. Um, and the pressure at the exit is 7 bar. The volumetric flow rate, so this isn't the mass flow rate, it's by volume, is 0.06 cubic meters per second. And we want to calculate the mass flow rate at inlet 2, the mass flow rate at the exit, and the average speed of the liquid at inlet 2. And there's one more important bit of information that we have. This is steady state. Okay. So a steady state process means that the mass inside the control volume is staying constant. Okay. So steady state means that dm dt for the control volume is 0. Okay. So anytime you see steady state with these mass balance things, it just means the equation reduces to, so if you start with this, since it's in steady state, this goes to 0. And so what you're left with is just that m in dot is equal to m out dot. Okay, so anytime you see steady state, that's what that means in a mass balance calculation. And now we can start to put some of these things together. For ours, notice since we have 2 inlets, so we have this, and this goes to 0 because of steady state. And so ours reduces to m inlet 1 dot plus m inlet 2 dot is equal to m out dot. We already have mi1 dot. mi2, so what can we figure out about that? Well, this is, so at inlet 2, we have liquid water, with a known pressure and a known temperature. And so anytime you know 2 properties of a material, remember that if you have a website or a table that addresses that particular material, you can look up all the other properties. Okay, so I'm going to go to the website. And I'm going to put in so we want water, we want international units, um, temperature. This has to be in Kelvin. We have that it's 40 degrees Celsius, so this is 313. And then absolute pressure is in kilopascals. We have 7 bar, which is which is 700 kilopascals. Um, that is not right. 7. Oh, okay, thank you. I could see that wasn't right because it said that it's that it's a superheated gas, and we want this to be a liquid. Okay, so subcooled liquid or a compressed liquid, and so what we need here is the specific volume, and we can see it's 0.001008. So the website tells us that the specific volume is 0.001008. And now we can say that the mass flow rate is equal to the area times the speed divided by the specific volume. So that is, we're given that the area of the opening is 25 times 10 to the minus 4. We're trying to calculate this speed. And we're dividing by 0.001008. So this comes out to be 2.48 times that average speed. Okay, so we can't calculate that average speed yet, but that's going to go into our equation. And then we'll go to the exit. And we're told that this is saturated liquid water. At a known pressure. Well, if you're at a saturation point and you have a table or a website for that material, and you know one property, you can look up all the other properties. So I'm going to go back to this table, and I'm going to say that what we want is a quality of 0 because it's liquid water and a pressure of 700 kilopascals. And it says that our density is 0.001108. So the specific volume is 0.001108. Well, the mass flow rate at the exit is equal to so think about the mass of something is the volume times the density, which is the volume divided by the specific volume. So this is going to be the volumetric flow rate that we're given, divided by the specific volume. And so this comes out to be 0.542. And now we can go to the mass balance. Yikes. And at inlet 1, I mean, we know that the mass flow rate is 40. So we have 0 is equal to 40. Yeah.
You missing a 0 for the mass exit for the specific value for the dividing.
Oh, yeah, you're right.
Exit 54.
Yeah, I'm missing a couple zeros. Okay, 54.15, let's say. So we have 40 plus our rate of mass flow at the inlet 2, which is 2.48, times the volume at inlet 2, then minus 54.15. And now you can calculate that V. You can calculate the mass flow rates, everything you need. Okay, let's stop there. Anybody have any questions about that? So remember, changing